Um, what I want to talk about today is a new kind of method to derive mean field limits for particles and then multi-agent systems that we've been developing in the past few years. And because I've chosen the technical version, I'm going to focus very specifically on the case of the Keller-Segel model for chemotaxis. So the system looks like this. And you see the equation on the xi, right? So xi are the position of the particles. You have n identical particles, so we are tracking their position. And we are solving a coupled system of stochastic differential equation that has a very simple form. Because the derivative, right, of xi is what? First of all, you have diffusion. And diffusion is due to those Brownian motion or Wiener processes, the Wi, and they are independent. So each particle sees a different independent diffusion effect. They interact through the force term, which is just before. And the forces between particles are, again, have a very simple structure because they are just the sum of 2x2 interactions with some kernel that I'm going to denote K. And I removed, you notice in the sum, I removed the self-interaction, which is a bit more convenient because K, of course, in this talk is going to be singular. Now, the key point in this first equation is this 1/n scaling factor in front of the sum. What that does formally is very simple. It keeps, you have a sum of n terms, you divide by n, so formally it keeps that sum of order 1. Now, whether it does that rigorously and in what norm is the whole difficulty of the problem when K is not smooth. This is a choice of scaling, though. If I'm looking at a precise physical system, for instance, what I will have is I will have a distribution of position of the particles, and I will have physical constants that determine the strength of the interaction. Now, I can rescale the initial position so that everyone is in a box of size 1, which is what I'm doing here. Pi d is the torus, and I'm choosing the torus for simplicity because I don't want to consider boundary conditions here. There would be actual technical difficulty in considering the full space, but let me skip that. So I can rescale and get into a box of size 1. And I can rescale time. But there is no particular reason why, when I'm doing all those rescaling, I would get to a coefficient here that is exactly of order 1/n. So this should not be seen as the only possible system of interacting particle, even with those simple 2x2 interactions. It is one possible system. And as I usually say, it should be seen as the first or the simplest interesting one. Because either here you will have a coefficient that is smaller than 1/n, in which case you expect that asymptotically the forces will disappear, not very interesting, or you will have a coefficient that is larger, much larger than 1/n, and then you expect very strong forces. Sorry, was there a question?
Now it's fine.
No, okay. All right. Now, the key case that I'm going to look during this talk is the case of gradient flows. So gradient flows, K is the derivative of the potential. And in particular, what I really want to do here is take as potential the Poisson law. So K is minus Laplacian of V, and V is, well, in 2D proportional to log of X. Now, you can add perturbation to that. In particular, if you're on the torus, you need to periodize the thing. But this is the singularity that I'm going to be interested in. Now, one key thing to observe here, if you have gradient flows, is that the sign that you put in front of V is absolutely fundamental. And here I put the wrong sign. Right? Log x is negative when x is small. So what I have here is an attractive interaction between particles. And I'm saying it's the wrong sign because it's, of course, a lot harder than if we had repulsive interactions between particles. Now, what this system does, it's very well known. And formally, its mean field limit leads to the famous Keller-Segel system, which has been obtained, for example, for chemotaxis. Now, one last remark before I show you that system. Here in general, I'm going to fix the viscosity over diffusion coefficient sigma. This is for simplicity. I could allow the sigma to also scale with a number of particles. All right, what do we want to do with this? Well, in general, if you start from a system of many particles, there are several things that you could think of doing. And many of them are actually quite difficult. This starts with the basic question whether the system that I wrote on the slide before is well posed. This is a coupled system of SDE with a singular interaction. So what can we say about the existence or the uniqueness of solution for a finite n, right? Even a small n. And it turns out this is a very, very difficult question to which I don't have any very good answer. The best result so far is a paper by Fournier and Jourdain, and they can only prove this when the diffusion strongly dominates the dynamics. So with my scaling, it's the case where lambda is strictly less than sigma. And to realize some of the difficulty here, you have to think that there's a Brownian motion on each particle. So from times to times, a pair of particles will get very close. Right? Brownian motion, especially in 2D, it will get you in any neighborhood of 0. And what happens when a pair is close? Well, what happens is now you have a singular attractive interaction. And if this interaction is too much and it can, bring them into a collision, then that's the end. You cannot have any reasonably strong solution to the SDE system. So this is already a difficult question, but I'm essentially again going to bypass, and I'll explain a little bit later how we can bypass this question and still answer the mean field. So what I'm interested in is the third point here, which is the mean field limit. And the point is to explain and try to quantify how this previous system can be shown to be close to the limit, which is the system I've written here. Right, so the limit is given by a continuous system governed by the one particle distribution, which I'm going to denote rho bar in this talk. So rho bar is a probability distribution. It's a non-negative function with a total mass 1. And it satisfies an advection diffusion equation, right? You find the diffusion here. That's the reason why I had chosen the square root of 2 sigma in the slide before, so that I'll get sigma here instead of sigma squared over 2. And it's advected by a velocity field, and the velocity field is given by our gradient flow. All right, so I think most of you have seen stuff like that. So what is a little bit specific about that particular example? So what I've done here is I've just taken the same system, right? But now I've used the fact that V was lambda log x, so connected to the Poisson kernel. So let me now, just for this slide, go to RD so that, the green function for Poisson is exactly log x. So I'm in R2. And now the equation I get is this. Right? And this is the Keller-Segel system. And it serves as a bit of a toy model for chemotaxis. Now, chemotaxis just means movement driven by a chemical. And what this system does is something very simple. It assumes that you have, for instance, a certain number of bacteria or cells, and you have a certain chemicals in the environment that those bacteria live in. And let's denote by phi the concentration of this chemical. Now, what the first equation does is it says the bacteria follow what? Well, they follow a diffusion process with coefficient sigma, and then they are driven with the concentration of the gradient of the concentration of this chemical. Right? So U is equal to gradient phi. What that does is they are trying to go toward the higher concentration. Right? So if there's a gradient, they will follow the gradient up. Now, if this chemical is something that they are looking for, that they are attracted to doing it. And then what we have is we have a Poisson equation on phi. Now, phi is a chemical, so it's something that will diffuse in the environment. And in this case, what is assumed that phi diffuses much faster than the bacteria are moving. So instead of having the parabolic diffusion equation here, we assume that phi reaches a stationary state immediately. So that's why you don't have a dt phi. Now, the key thing here is phi is produced by the bacteria themselves. And this is the reason why lambda, this is the case when lambda is positive, right? So this is, the right-hand side here is a source term for phi. And what this does is it starts creating very interesting phenomena, because what happens is the bacteria try to go where the concentration is higher, the concentration of the chemical is higher, but they also produce the same chemical. So you have a feedback loop where the more bacteria you have at a place, the higher the concentration, and then the more you attract other bacteria will produce even more and so on. It's a very natural question to ask whether this phenomenon is controlled or not. And the remarkable fact for this very simple model is that we can answer that also in a very simple and complete manner. And there's a huge literature on the subject. I refer to the paper by Dolbo and Pertam, for instance, which sort of synthesize this in 2D. What happens is the following. If the strength of the interaction, lambda, is small enough, then you have global existence. If that strength is larger than the critical value, which is 4 sigma, and in general, if we were taking the same logarithmic singularity in higher dimensions, so d is different by 2, what we would get here is exactly the same analysis with 2d instead of 4. So if lambda is strictly larger than 4 sigma, then you have blow up infinite times. Now, many of you probably saw something on the Keller-Segel system, and you probably remember something like the critical mass being 8 pi. Right. And this is the same scaling. Okay, it is just that I have a different normalization. Because since I'm doing the mean field limit, my rho bar is necessarily a probability distribution, so total mass is 1. So the mass actually goes into the sigma, into the lambda, sorry. And you see that I already have a 2 pi here in the right-hand side, right? So the 4 becomes an 8 pi. Now, this analysis, the whole analysis of this is based on the free energy of the system, which is a combination of the entropy, the integral of rho bar log rho bar, and the interaction energy, which is this integral of log x minus y rho bar x, rho bar y. Again, log is negative, right, here. So the sum is actually a difference. And you can have compensation between the two energies. The critical point where you go to blow up instead of having global existence depends on which of the term can dominate. And if lambda is less or equal than 4 sigma, what happens is the entropy part, the integral of rho bar log rho bar, dominates the overture. Okay, before going into the actual technical side, let me give you a bit more context. This is a slide that I'm reusing in essentially all my talks. So I'm sorry, many of you must have seen it already. I think it's very informative, though. So this is the reason why I'm making a lot of use of it. And this is the question, okay, so I'm taking the limit n tends to infinity. What do I mean by taking the limit n tends to infinity? How big exactly is n? And I'm giving you some of the ranges here that you typically observe. And what you see is that in physics, n can actually be very, very large, right? Typically, think Avogadro number. So 10 to the 20, 10 to the 25 are common scales. But if we're doing biology, for instance, Keller-Segel system, it's probably more relevant. Populations are already lower. And the population of bacteria, for example, will typically range between 10 to the 6 and 10 to the 12. Usual joke is if you have an infection below 10 to the 6, you will not be able to see it, to detect it. And above 10 to the 12, you're probably dead. So now what's interesting about those numbers is, let's say 10 to the 10, this is not so big. So we have to be careful when we're taking the limit. That this may not actually be accurate. Right? So if I have a soft result that describes the limit as n tends to infinity, I may face problem in practical situations because if I tell you, well, n is actually 10 to the 9, is it good enough to use the result or is it not good enough to use the result? And that's one reason why when you can do it, sometimes you cannot. But if you're able to get quantitative result that tells you, well, for this n, this is how close you are to the mean field limit, it is so much better. Another general comment, which is, of course, what we're doing by taking the mean field limit is we're not trying to describe the trajectory of every individual particle. We are trying to describe the macroscopic behavior of the system altogether. And from a physical point of view, people like to talk about observables, and observables are quantity like the ones I have written here, right? So they are average of a function of the position of the particles, or maybe average of the functions of two positions if you want to calculate correlations. All right, let's go a little bit into the classical literature for this problem. And let me start with a deterministic case. By the way, it should be sigma and not epsilon n. Sorry, there's a typo here. Now, in the deterministic case, the classical result assumes that the interaction kernel is Lipschitz. And there was a series of papers in the late 70s. I'm giving the names here. I'm sure, again, if you've seen a talk on mean field, you've seen those names. That provide a very, very nice explicit stability result. And what happens is the following. You can easily compare two solutions by using the empirical measure. So the empirical measure is essentially a counting measure for the system. It's defined like this, right? So if I have n particles, I'm just summing the Dirac mass at xi. So what the empirical measure gives me is the empirical measure of a set, right? Is simply the proportion of the particle that have position in that set. And I can do that for a different system with a different m, right? And then I can compare the two. And it turns out I have this. The proof is not particularly difficult once you understand how you have to do it and which framework you have to put. And that would be perfect, right? Because what it tells me now, if I let m tends to infinity, for instance, then I'll get a continuous approximation of the initial condition here. And well, this will give me an explicit quantitative estimate of convergence to the mean field limit. You actually have similar results in the stochastic case, but then you have to add, here a 1 over square root of n, because the stochastic case, you cannot have an exact solution. And again, basically, the proof of that is to go back to Gromval lemma and do a Gromval lemma for either the ODE or the SDE system in the right manner. Right. I still have one comment here aside the big one that you've already seen. So let's say I want to do that, right? And let's say I want to do that by doing an approximation. So I have mu n with a large n, and I want to solve the system. I want to approximate the system by solving a lower system. So m is smaller than n. Well, I can approximate the sum of Dirac mass by a sum with less Dirac masses. If I do that, the sort of best estimate that I can get on those measures in this W minus 1 distance is m to the power minus 1 over d. And the way I'm doing this is sort of building a classical numerical mesh by cutting my torus into a certain number of boxes, right? And if I have m particles, then the size of each box should be of order m to the power minus 1 over d. And that's what gives me the order of approximation here. Now, sometimes people use different norms that such time distances are very popular. You essentially get the same approximation. This is actually not such a great question if the dimension that we are looking at was very large. So this is something we should have to be careful with in a case like that. But the big objection with the method is, of course, that it requires K to be Lipschitz. And our K is far from being Lipschitz. I mean, K is a derivative of a log, right? So K behaves like 1 over x. So gradient K behaves like 1 over x squared. We are missing 2 derivatives at least for K to be Lipschitz. There's still a relatively rich literature around this. I mean, first of all, I don't want to undersell the Lipschitz case. If you really want to understand what's going on, the type of framework you have to put, this is still very important. Something that has been very frustrating is that deterministic systems are actually much better understood with singularity than stochastic system. And in particular, we had the mean field limit for the 2D Euler, well, for almost 20 years now. And the mean field limit for the 2D incompressible Navier-Stokes was actually a result that we got with my students 3 years ago. So that gives you an idea of the difference in time that was required to understand the stochastic case. Concerning the Keller-Segel system, there are already some results. And again, the best one is probably this paper by Fournier and Jourdain. You have some limit, again, in the case where the system is strongly diffusion dominated, so lambda is strictly less than sigma. But it's a very weak limit. It's not quantitative, but the notion of solution that you get at the limit is also too weak to even have uniqueness. So you don't have even propagation of chaos within that system. So instead, what we try to do here is combine two recent approach. The first one was this paper that we did with my students on 2D Navier-Stokes. And what we took is a very different way of looking at the problem, and I will go back to that in the next section, so I will tell you a lot more, of course, by using the Gibbs entropy of the system and working at the level of the Liouville equation. Now, what we had is a very nice result with optimal rate of convergence, 1/square root of n. And we only required that k be in W minus 1 infinity and the divergence of k be in W minus 1 infinity. Now, if you have an incompressible system like a 2D Navier-Stokes, right, divergence k is 0. So the only condition is k is in W minus 1 infinity. Minus 1, right, instead of plus 1. So here are the two derivatives that I said we were missing, right? They are here. Instead of Lipschitz, now you go to W minus 1 infinity. That's it. You've won the two derivatives. Now, the k from the Biot-Savart law, which has exactly the same singularity as in the Keller-Segel, works. The issue is if I want to do gradient flow, right? So if k is the derivative of something, now this condition on the divergence is very hard. Because divergence of k in W minus 1 infinity, well, that's Laplacian of a potential in W minus 1 infinity. So that essentially means that k has to be bounded. And we don't have that. So this was a little bit frustrating, but the gradient flow structure itself was not working very well with our approach. And even though the singularity seemed to be the same, it was not because of this. So we couldn't use what we've done in that case. The second recent breakthrough is, of course, a series of contribution by Serfati and Durings and Serfati. Now, this is a deterministic case. So there's no diffusion sigma is equal to 0. And what they've done is they have used also the physically relevant quantity, which in that case is the potential energy of the system. And they built an entropy out of that. So they use a modulated potential energy. And what that gives them is the mean field limit for all Riesz gases. So Riesz gases are deterministic gradient flow with a potential that is polynomial. So this is this guy. Those are repulsive, okay? V is positive. But they can even go further than Poisson singularity. The only requirement is that alpha is strictly less than D, which is extremely weak. Right? That means that the gradient of V might not even be integrable. So this was hugely successful, but there are two issues. And obviously you can guess them, plus they are written. The first one is theirs is a deterministic approach. If you put noise into it, it does not react well with the potential energy. And the second is we actually have an attractive potential. And how do we do that? Now, if there's no diffusion, putting a singular attractive potential in the dynamics creates very singular behavior, and you would automatically have blowups, for instance. But if there is diffusion, you can hope that the diffusion can control part of the attraction, and that's the whole point in the control of blowup and Keller-Segel. All right. So this is our new result. And it's a little bit, I wrote it in a little bit of a technical manner to give you also an idea that it goes beyond just Keller-Segel. So what we can have is, first of all, you can add any smooth part in the potential. That's no problem. It's not a very big surprise. The singular part, you can have something that, well, first of all, can have any repulsive singularity. But if you're putting something attractive, then the most that you can do is a singularity in log x with a strength that is strictly less than 2d sigma, and this is exactly the blow-up criterion for the limiting Keller-Segel system. Now, you notice that here I'm only asking for an inequality. If there is an equality there, you can ignore what comes below. But if you put an inequality, then I also need some control on the Fourier transform of the potential. And there's a bit of this technical estimate here that gives you some indication of the decay of the Fourier transform. And mostly what I need is when I take derivative in psi of a Fourier transform, then this decays one order faster than when I'm not taking derivatives. And again, you can have perturbations for this. This is in the non-vanishing viscosity case. If you have vanishing viscosity, then of course we cannot have now attractive parts. So it's only repulsive singular. You have a bit more of a technical assumption here. We've actually explained that in a seminar article, Polytechnique, so you can find the text online if you're interested in this case. I will mostly go over it fast. It extends quite a bit the Serfati result in that case. The theorem is the following. So assume that we have all the right conditions that I've just listed. And now what I can do is I can compare the joint law, rho n, of the system. So rho n is a crazy function. It lives on a product space. So it lives on the torus pi d to the power n, because there are n particles. And well, what should I compare this to? Well, I should compare this to what I expect the law to be at the limit. And if there is propagation of chaos, then everyone should be independent. So the law at the limit is this rho bar n. I take the solution, rho bar, to the limiting system, and then I tensorize it. Very simple. So we would like to say that in some sense, rho n is close to rho bar n. And this is this inequality here that you have. All right, so there are two quantities that show up here. The first one is the relative entropy, the scaled relative entropy. This 1 over n, rho n, log of rho n. There shouldn't be a 0 here. It's rho bar. Sorry, another typo. The second quantity is this Kn, which is the modulated potential energy that is used by Durinx and Serfati, which I can write like this in that case by using the empirical measure and comparing with the empirical measure to the limit. And so this Kn is the expectation of it. Now I'll come back to those quantities in a minute, so don't worry too much about them now. Now, one thing I want to stress is, contrary to the Serfati case, because we have attractive singularities, Kn might not be positive, and in general will not. And this is why what you see here is I'm not summing Hn and Kn, I'm summing Hn and the absolute value of Kn. And in particular, what I need to have at the initial time is that independently Hn goes to 0 and Kn goes to 0. What this is going to do is this is going to give me a quantitative estimate on those guys at any later time. Now, as usual in those mean field limits, this is a short time estimate, so I have an exponential growth. If you're asking what is the norm of k here, well, the norm of k here corresponds to all the constants that show up in those assumptions.
Okay.
Okay, so what?
Good.
Right. An easy consequence of this result is the following inequality that is at the bottom. You can see the bottom of my slides, right? So this is something, again, I will explain a bit more why this happens. So this compares now the marginal. Right? So the marginal is something, rho n k is something that you simply get by integrating rho n against the n minus k last variables. So rho n k is actually the joint law of k particles out of n. And if k is fixed, what this result tells you is that you can compare in L1 this marginal with the product of the rho bar, right? So rho bar tensorized k times, and you have a polynomial convergence net. So that completely tells you how the system is behaving statistically. Right. This is the vanishing viscosity case. Let me bypass that. And let me try to give you a little bit an idea of what's going on here in the next 15 minutes. So, well, we are looking at the joint law. All right. We can actually write a very simple equation on the joint law. Now, you can call that the Liouville or the forward Kolmogorov equation. And it treats something like that, right? This is here, where the operator Ln is that object. All right, so this is relatively simple. This is just a linear advection. So this are just the characteristics. And I'm saying that if you give me a system of ODE, I can write an advection equation on this. And because I have SDs, so I have diffusion, well, I should write an advection diffusion equation with the corresponding Laplacian terms. This is both a simple and a crazy equation at the same time. It's simple because it's linear, it has a very simple expression, but it's an equation in dimension d to the n. Dimension d for each variable, and I have n variables. What this does is it describes very well the statistical information of the dynamics. What it does not do is it does not follow trajectories. So this is not the whole system, and I have to insist on that. If you wanted the whole system instead of the joint law at a given time t, what you should look at is the joint law of the trajectories. That's the whole system. And the joint law I'm using here is if you want the projection of that joint law of the trajectories at some time. So there are things that we are throwing away when we are looking at that. And this is probably the reason it works. Because we're not trying to get in precise information on each trajectory. Now, another quick word about this, as I mentioned while posing this. Well, it turns out we can easily, not so easily, but we can get weak solutions to this equation. And we can get weak entropy solutions, meaning weak solutions that have the right decay of the physical quantities like the total free energy. And those are the solutions we're using. So we're not working on solutions to the original SD system. We're working on weak entropy solution to the Liouville equation. Those may not be unique, by the way. We have no way of saying that. But the previous theorems apply to any such weak entropy solution. So there might be several of them, but they will all have the same limit. All right. Let me explain now a little bit the result before we go into the method. Why do I like the Gibbs entropy so much? Now, if you're thinking of the Liouville equation, and let's say that instead of a gradient flow, I'm taking an incompressible flow. So divergence of K is 0. Then I have a maximum principle, you know, on this equation. Maximum principle tells me that the L-infinity norm of rho can only decay in time. This is a wonderful estimate. So why aren't we using maximal principles like that? The problem does not lie with the equation. The problem lies with the scaling of the problem. Right? Let's say that rho n initially is tensorized as well. Then this L-infinity norm will behave like some constant to the power n. So what I get out of that is that this L-infinity norm behaves like constant to the power n, and there's nothing I can do with this. This doesn't say anything on the marginal, for instance. So while there are several quantities that for a fixed n would make sense on the Liouville equation, when you're looking at which quantities make sense as n becomes large, there are very, very few of them. But the entropy does. And here is, for instance, a key fact on the entropy, which is very simple to prove. It's just the subadditivity of this entropy. So the only thing you're using here is the fact that x log x is a convex function. So I'm looking at the entropy of the full law, rescaled by 1 over n. And I'm saying that this controls the rescale entropy of all marginals. Again, rho n k is the integral of rho n with respect to the n minus k variable. So this is how I get the final conclusion to my theorem, for instance, because I have an estimate on the relative entropy. Now, it turns out if rho n bar is tensorized, I have the same inequality. So the estimates on the total relative entropy controls the relative entropy of any marginals. And now I'm in finite dimension, right? I'm on the torus pi d to the power k with a finite k. I can apply standard Csar-Kullback-Pinsker inequalities. That tells me that if I control the entropy, I control the L1 norm. And I deduce a control on the difference of the L1 norms. So this is very simple and comes for free. However, I insist here, this slide was in the incompressible case. Divergence k is equal to 0. The problem when divergence k is not equal to 0 is the entropy is not propagated, for instance. So we have to do something else. And what we've done, and this comes also from a previous paper with Didier in fluid mechanics, where we had used weighted norms, is we tried to use a weighted relative entropy. And we want to choose the weight so that we bring back the system to a sort of self-adjoint structure on the interaction. And if you want to do that, it's relatively natural to try to introduce the Gibbs equilibrium. So this is the Gibbs equilibrium for the whole system. Again, I think that here, I mean, I have to remind you here, V is negative. It's log x. So this is actually a positive singular, right? So when I'm taking the exponential, this is actually a singular object. Now, I cannot just stay at the level of the Gibbs equilibrium. And the reason I cannot do that is, well, because we're using relative entropy. So it's not enough to put the original Liouville equation in a self-adjoint manner, we also have to correspondingly try to symmetrize the limit. So what we are considering is a sort of mean field limit of the Gibbs equilibrium, which is this G of rho bar n. And this is a bit of a delicate object because, right, if I'm, well, you see what I'm doing here, right? This sum I replace by a convolution. And it makes sense. But, of course, this was a stationary equilibrium for the system. This is now time dependent. Rho bar depends on time. And it's not a stationary solution for the limit. You observe as well that I'm adding here this term. And this is needed if you're actually doing the limit correctly. Now, one thing that is obviously maintained is that this G bar n, G of rho bar n, is tensorized. So there's the G of rho bar, right, which is just this guy, and the version, the line above, is just the tensorized version of this. What are we doing with those? What we're doing with those is we are weighting the relative entropy with them. So instead of comparing rho n and rho bar n, now I'm comparing rho n divided by Gn to rho bar n divided by G of rho bar n. And that's the object we're working with. And there's a very simple interpretation of this object that also strongly suggests this is the right physical quantity. I can divide it into two, right, by putting on one side the standard relative entropy, the Hn, and then on the other side I have, so this is this, and then on the other side I have the Kn, right, which is an expectation of a log of the ratio of the Gibbs equilibrium from the limiting Gibbs equilibrium. And if you look at what Kn is, it's actually the modulated potential energy that is used by Serfati. So this is extremely convincing. And what that means is this En that we are using is a sort of modulated free energy for the whole system. And of course, if we are in an advection diffusion case, the free energy is the right physical object. You have to combine them well, right? So it's not just any linear combination of Hn and Kn that will work here. It's this particular linear combination. And right, you note the scaling here. The 1 over sigma, I'm not putting just any temperature. The temperature is fixed because we have diffusion. All right, so the first big step is to, do a formal calculation and ask, well, can I find a time evolution of this quantity? This is a painful calculation to make, but if you do it right, it has a super simple expression. And you see it here. The time derivative of this is less or equal because we only have entropy solutions, not strong solutions, to a dissipation term. This is the corresponding Fisher information, the rescaled weighted Fisher information, minus this thing. So this involves the gradient of V, okay, which is K. And it's another quadratic quantity into mu n minus rho bar. Just like the potential energy was a quadratic quantity of this type. But it comes with this factor here. And something that I want to emphasize, the precise factor here is not very important. What is absolutely important is that rho bar is smooth because it's a limiting solution, and G of rho bar is smooth because it's built around this limiting solution. So those objects here, those functions are smooth. All right, so what do you want to go from there? Well, there are two things you want to do. Basically, what you want is to build a Gromval estimator on that. And I need to do two things. I need to control the right-hand side in terms of the left-hand side. So I need to bound the right-hand side in terms of En. This is actually easy. It's easy because if you combine what we did before with Zenfu and what Serfati did, then you have the answer. The hard part is actually, if I want to do a Gromval estimate based on En, I better make sure that En is a positive object. So what I would like to have is an estimate like this. I would like to know that En can be bounded from below, right, by the relative entropy. Okay, so if I put everything all together, then what I have is something like that, right? This is what I would like to prove. The problem is, as far as I can tell, this estimate is false. Instead, what we prove is the following. Now, the difference here is that instead of looking at the whole potential energy, I'm truncating and I'm only looking at the short range interactions between particles. And then the estimate is true. Aha. That's interesting. Because that's probably not what you were expecting when I told you the estimate is false. What you were expecting when I told you the estimate is false is that, well, it's false because of a singularity of the potential. And I'm telling you, no, with the singularity of a potential, we can actually prove it. The issue is not with the short range. The issue is with a long range contribution. Now, I don't know how much you followed. For those of you who did, you're probably thinking at this point, the long range part of the interaction is smooth. So there shouldn't be any problem with it. And yeah, that's how we do it. So what we actually do is we don't consider in En everything, we only consider the short part. Sorry. We only consider the short range part. And then the long range, we do a perturbation argument. All right, let me skip this one. And let me explain a little bit what happens with this last estimate. This is a large deviation inequality. I'm not sure how familiar you are with large deviations, so I sort of gave a very elementary introduction here. So let's take a functional which to any probability measure associates a value which is possibly plus infinity. In our case, it's this guy that I'm interested in, right? So it's this short range potential energy. Then what the large deviation theory tells you is that the behavior of object associated to that will be connected with the following large deviation functional. And in particular, it is key to show, in our case, that this IF, which is the maximum over mu of those things, is 0. And this is not true. This is what is not true if you add the long-range interaction. But it will remain true if you only have the short-range interaction. Now, unfortunately, we cannot use directly the large deviation theory because the large deviation theory requires F to be continuous on measure. And of course, if we have a singularity, that's not going to be true. So instead, what we're doing is we can regularize the F by convolution and still control it. And there's a lot of work there that I'm going to skip. And what we get is something like this. Now, here I've done it poorly because I've just tried to use this and to combine with a large deviation functional. And if I do it poorly, I don't get the optimal estimate on lambda. I get lambda strictly less than d instead of lambda strictly less than 2d. So this is where a lot of the technical difficulty comes into the paper. We actually have to redo the whole large deviation stuff so as not to lose. But I'm going to point out the following consequence of the Hardy-Littlewood sub-LF inequality. If I truncate short range here, then I have the following inequality. And this is what corresponds to my IF equal to 0. All right, I should finish now.